Okay, yesterday I tried to do the 9-6 video, but it didn't work out too good. So I was going to recap anyway today. Maybe that's all we really needed was a 10-minute explanation of what I said yesterday, not a 45 one, 5-minute one. But yesterday was part of kind of storytelling why math includes polar forms, and also how sometimes polar forms are actually the preferred forms. Okay? So think of yesterday and today as a single story, okay, with 3 acts, like a play, 3 acts, okay? In day 1, we had 2 acts. Act 1, scene 1, okay, it's a play. In Act 1, scene 1, we said, look, we know how to convert equations to polar from chapter 8, right? But it seems like when we do that with conics, they get real ugly. So we asked the question, very logical question, is there ever a time when you convert and you actually get a real pretty, tidy, simple answer? And actually there's a yes to that. But you have to place the focus at the pole, okay? So whether it's a parabola like this, or maybe it's an ellipse like this, or whether it's a hyperbola like this, it turns out the polar format, the r theta version, is actually very, very tidy. Real simple, real neat with only 2 parameters. 2 numbers that are special. Okay, so we'll see that today. But that's Act 1. I just wanted to convince you that polar form could be desirable if things were properly designed. Okay, and then in Act 2 of the story, it's also day 1, but in Act 2, I sort of changed topics. And you might have been like, what is he doing? Why is he totally changing topics? Well, what I did was I picked a directrix line and a focus point, and I did this game 3 times. Okay, so D is directrix, right? And F is what class? Focus. 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 Okay, and we played 3 different games. In the first diagram, we drew points that were equidistant from F and D. So it actually produced a parabola like this. And what's interesting is the distance from the focus to a point is always equal to the distance from the point to the point to the directrix. So in other words, these 2 green segments are identical always. It doesn't matter where you draw them; they're always the same. So whether you draw them there or whether you draw them over here, that's not a very good scale, you know. But the idea is they're supposed to look the same. So we write that mathematically like this: the distance from the focus to the point divided by the distance from the point to the directrix is 1. The ratio is 1 because of the same length. Okay, then we did in the second game, we caused our points to sort of hug closer to the focus and further from the directrix. What happened was we got an ellipse, okay? And we didn't just arbitrarily pick distance. What we did, if you remember, was if this distance was 3, we made this distance 6. And if this distance was 10, we made this distance 20. We intentionally designed it where point P is twice as close, I said that wrong. Point P is twice as close to the focus, as it is from the directrix. Or you can say it's twice as far from the directrix as it is to the focus. So we purposely set it up this way, and these are all like ratio half. So if you set up the equation, the distance from the focus to the point divided by the distance from the point to the directrix, we always get 1/2. And this actually forms an ellipse. I'm not proving that it forms an ellipse, I'm just saying it forms an ellipse. There's a little bit of gimme on this. Like, some of it's just facts from Mr. Shorday, you know. But I'm trying to also convince you. I worked very hard. You saw me up here with my ruler, painstakingly trying to plot the points, and it sort of looked like an ellipse, right? It would have been a really good ellipse if Mr. Shore had been more careful. Okay. It was not for lack of effort, though. I tried very hard. Then the third diagram was obviously the third case, that's your hyperbola, right? In the hyperbola, the points hug the directrix more, actually. They're closer to the directrix, and the distance is, like if this is 4, this is 2, kind of thing. Or if this is, 5, this is 2.5. So it's just sort of the reverse game of our second ellipse game. And this produces the hyperbola. And mathematically, we would just write df of the distance from f to p divided by the distance from p to d is 2 over 1. Okay, now I picked 1 and 2 ratio, but honestly, it didn't have to be 1 and 2. I just thought that'd be convenient. It just needs to be, for an ellipse, it needs to be that the distance is from f to p or less, and the distance is from p to d. So it could have been 1/2, it could have been 1/4, it could have been 3/4, it could have been 9/10. You see what I'm saying? It could have been pi over 4, that's less than 1. And in the hyperbola case, it doesn't have to be 2 and 1, it could be 10 and 9, you know what I mean? Obviously, when you're designing the shape, you never change that ratio, right? You don't want to be like doing, oh, this is 3 and 6, and the next one will be like 4 and 12. You don't want to change from a ratio of 1 and 2 to a ratio of 1 and 3 halfway through your sketch. As long as you keep that constant half ratio, though, you'll create this ellipse. If you keep a constant 2 over 1 ratio, you'll create a hyperbola. Okay? All right, so that was Act 2, and it seems very distant and different from Act 1. So that's because you haven't seen the rest of the story. You haven't read the end of the book. The end of the book is Act 3, the end of the play. So what is the end of this play? Act 3. That's today, day 2. So this is where everybody takes notes, right? Because you haven't seen this part yet. So why is this sort of making such a big deal of Acts 1 and 2? Like, what does it all mean? It's like 2 different plot lines, and they're going to come together. It's like a Dickens novel, right? There's like all these different characters, like, oh my goodness, they all tie together in the end. So cool. All right. So this is the story of math. So what about Act 3? Well, I think it's time to draw our very first specific conic. Okay, so we'll just draw our xy axes like this. Our plan from Act 1, remember, was to put the focus at the pole. We cannot change that. I'm not sure we want to. Let's leave it there. Focus is at the pole. Oh, by the way, Mr. Shore is saying pole. Do you guys know what I mean by that? Yeah, it's just another fancy way to say origin. Okay. All right. And just to kind of match Act 2, let's put our directrix to the left of the focus, just like I did in the games I played in Act 2 yesterday. So we'll put our directrix here. So this is the directrix. This is the focus. And let's label our axes so we don't get confused. This is our x-axis, this is our y-axis. Okay, so there's this conic, right? There's this conic, and the conic fits between these because, it's like the focus is like a fly about to get eaten, So there's this conic like that. What do you guys think? Is Mr. Shore sketching a parabola? Or is it a hyperbola? Or is it an ellipse? What's he about to finish drawing here? Okay, we don't know. That's the whole point. I don't want to tell you what shape this is. I don't want you to think of it as necessarily an ellipse. Maybe Mr. Shore will finish it and make an ellipse. Or maybe he's not planning to. Maybe it's more of a parabola. Or maybe it's a hyperbola. The whole point of today, one of the points of today is it doesn't matter what conic it is. The fly is always getting eaten by the Venus flytrap, right? So there is a bit of a clue here. When the vertex is real close to the directrix, right, it more resembles this third game. If the vertex is closer to the focus, it would more resemble the second game. Ellipse. And if we see that our vertex is right smack between the reds, then it would be a problem. So it looks to me like we're building ourselves a hyperbola, actually. Although it looks a little curvy to be a hyperbola. Listen, the point is, I don't want you to think about where V is right now. I want you to focus on this. I want you to focus on the blue, okay? So isn't it true that this point P, x, y, is our units from the origin, theta degrees from the origin. These are the same r and theta we've been using all year long. Draw that. That's really important. You guys see that? Okay. This is the same r we used in chapter 5, chapter 6, chapter 7 a little bit, chapter 8 a lot. When we did complex numbers, we called it modulus. But we've been doing r for a very long time. Okay? This is also the same theta we've been using all these months. Okay? Nothing's changed in that. Same old variables there. Okay, because we positioned, the first thing we started with in this picture was the reds, it might be important to give that distance a name. So most math books use K, the ones I've seen, call this distance K. But our book calls it P, so I'm sorry about that, but I'm going to have to go with P so you can read your book. That distance is called P. That's actually what we started with before we even drew the blue. And then we've got that r and that theta. We're going to try to write our equation of a conic using r's, p's, and thetas. Okay? So I'm going to need your help a little bit here. Go ahead and finish drawing the rest of this triangle. Okay? So there is definitely a triangle here. Right, where this is x and this is y. And as we've seen many times before, x is r cos theta and y is r sine theta. Get used to it. Adjacent side will always be hypotenuse cos theta. And opposite leg will always be hypotenuse sine theta. That's going to be true in your physics class especially. You're going to use it all the time if you haven't already. Okay, so do you guys remember what we said in Act 2? That all conics have a DFP over DPD. Remember that? They all have a DFP over DPD. Do you remember what I called it yesterday just before the bell rang? Starts with an E. Eccentric. And it's the adjective. Or it's the noun, I mean. It's eccentricity. Yeah, it's a long word. Eccentricity. Right. So they all have eccentricity. Parabolas have eccentricity 1, ellipses less than 1, hyperbolas greater than 1. Okay, so what I could do is sort of just generally write, this statement would be true, the distance from P to F divided by the distance from P to D is called E. That's a true statement. No lie. But I would like you to update for this picture. So I'm going to pause the recording and let you work for 5 minutes at least. You need to fill in numerator and denominator. Look at the diagram. How far is P from F? Look at the diagram. How far is P from D? So I'm talking about these two distances, these two gray segments. I want to know this distance and this distance. Can you guys see that gray? I'll make it a little bit darker gray. So I need these two gray distances. You're going to put them in, top and bottom here. All right? And then we'll have our polar form of a conic. Okay, let me pause the recording. Some people are having trouble finding the focus. Where did we say the focus would always be on these problems? The origin. Okay, sorry about that. Try again. Okay, so good. We got r for the numerator. That's the distance from the point to the focus. Try to get the other distance now. This one in green. I'll give you a hint if you're stuck. Some of you are stuck. You can measure it there, or you can measure it here. Same thing. Okay, so we could call this distance in green P plus X or P plus R cos theta. We're doing the polar thing, so we're going to go with P plus R cos theta. And congratulations, this is the polar form of a conic. Which conic? All conics. All conics. I never told you what conic it was. Right? That means it's true for all conics. Okay? All right, take a moment now and isolate R. Nobody really wants polar equation looking like this, right? So let's try to get that r by its lonesome self. This was a hard activity for some earlier in the day. Let's see how you guys do. Okay, so it's a bit of work, but you should get EP over 1 minus E cos. Let's say that a couple times because this is it, the big daddy formula. Okay, let's say it together. Ready, go. R equals, make sure you always read the left side of equations, right? So R equals EP over 1 minus E cos. Theta. Naturally. Okay? All right, so this guy's really important. I want to just show you some wind plot simulations real quick. Okay? Hopefully this doesn't crash my computer. Okay, so I have typed in EP over 1 minus cos theta into my calculator. I have created two sliders. One is for E and one is for P. You're going to tell me what these two things mean. Okay? When Mr. Shore changes the P value, what happens to the conic? It shifts, right? It's also doing a little bit of squishy squish. You see it? Sometimes the two branches of the hyperbola are far apart. Sometimes the two branches of the hyperbola are closer together. What's actually happening here? Now go back to your drawing. Look in your notes. When Mr. Shore changes P, what is he changing in your notes? The length from? Yes. Okay, so what I'm doing is I'm moving the directrix back and forth is all I'm doing. What happens is the curve follows it, but it also tries to maintain this special ratio. That's why it doesn't always look the same. It's not just shifting. It's shifting and dialing at the same time. Okay, anyway, P is just a distance, and Mr. Shore is changing it. Okay? What I didn't show you in my wind plot here is I never showed you where the directrix was. So I was changing it behind your back, and you don't even know where it is. I assure you, it's actually between the branches. Okay? Don't worry about it. There's actually two of them anyway. I wasn't going to teach that today, but there are actually two of them, not one. Okay, so anyway, I was changing the directrix location. Now, what happens when I change E? Well, first of all, do you guys remember what E stands for? Eccentricity. So it wouldn't make any sense to have any negative eccentricities, correct? Okay. I can't have negative eccentricities. So let's set a minimum eccentricity of 0. So I just set that on here. And a maximum eccentricity of 1. Now I'm going to auto-cycle. I'm going to let the eccentricity range from 0 to 2. Not 0 to 1, 0 to 2 I mean. I'm going to slow that sucker down so you can see that this happening. So E is going from 0 to 2. Still a little too fast, believe it or not. Okay, maybe the auto cycle is a little confusing because it keeps repeating itself. Let's just start at 0. We'll just hand slide it over. Right now R is 0. What do you see? Nothing. Okay. What is this thing? Ellipse. Right now my E is 0.6, 0.7, 0.8, 0.9. Zoom out a little so you can see it better. Move my sliders away. See it? E is 0.9. Here comes 1.0. Whoa, change of conic. What is it? It's a parabola. Okay, let's keep going. 1.1. Whoop. What just happened? Hyperbola disappeared. 1.2, 1.3, 1.4, 1.5. Notice the high eccentricity hyperbolas, and there's no limit how big I can go. I can go up to 1 million if I want. What's happening to my hyperbola? Okay, the branches are approaching each other. Do you think they'll ever reach each other? No. I've been clicking, I clicked like 20 times and it's only moving a little now. So they're going to sort of asymptotically connect. They'll never quite make it. Also, it's getting wider, right? Like the branches are wider, more like mellow looking. They're not so sharp looking. Okay, so you can think of E as sort of the conic determination factor. You know, E is less than 1, it's an ellipse. If E is greater than 1, it's a hyperbola. If E is exactly 1, we get the parabola. that's just kind of visual confirmation of what I said back in Act 2. Okay, but see, those are the only two parameters, right? If Mr. Shore changes E, he changes the conic. If he changes P, he changes the distance to the directrix. This is actually simpler than the standard form we used before. Because in the standard form we used before, there was H, there was K, there was A, there was B. Remember, 4 parameters. All right? In all fairness, though, these ones are all centered. Focus at the pole, you know. So they are pretty specialized, I guess you could say. All right, let's do some examples now. How would you answer this question? So let's see. Let's say I told you to find the directrix, vertices, foci, center, intercepts, and intercepts of the following. Sorry, my handwriting's pretty messy with the stylus. I don't know what my excuse is on the whiteboard. It's pretty bad there too. Okay, so anyway, for part A, we're just going to keep it simple. It's going to be 1 minus, and then let's do 2 minus 3 cos theta. Actually, let's do this. Let's make the top a 3. So make it a little bit easier. And we'll make this a 1. So Mr. Shore makes it, that's too simple. We'll make the top a 2. Okay, sorry about that. I had to really think about what I wanted for this problem. I want the top to be a 2. I want the bottom to be a 1 minus 3 cos. Sorry. Okay, okay, so do you recognize it? Would you recognize it if you saw it on the homework or test, quiz? Well, it does have that number over 1 minus number cos look, right? I just had you say this out loud. It was EP over 1 minus E cos. So what you're staring at is an EP on top and a 1 minus E cos on the bottom. Okay? So this represents EP, and this represents 1 minus E cos. Can you tell me by just examining what E must be? 3 is correct. So just by direct observation, E is clearly 3. See it? And we do this in standard form too. Like when we see the H, we know where the H is. Like we always look for the H, right? Here we're now looking for the E. That's the first thing we do. Hunt it down. Okay, we just determined that E is 3. That answers some of my mental questions, because if E is 3, I think I know what kind of conic it is. Don't I? It's a hyperbola. Why? Correct. 3 is greater than 1. That means it's a hyperbola. Also, it has the exact same format as this previous drawing. Number over 1 minus number cos. In other words, it's going to look quite similar to what I just had on the board a minute ago. So let's get started. This is just figure 1. Figure 1. Okay? All right, so in figure 1, we're just declaring that it's hyperbola and it opens to the right. So this is a focus. Actually, I'm gonna put my F right here. So there's my focus and my directrix. We know it's a hyperbola. We saw in Act 2 that means it's going to be kind of closer to the directrix. Okay, this is like figure 1. Please don't give me this as a final graph. That doesn't even look like hyperbola. We need some distances figured out here, okay? So we just learned that E was 3. But look at the numerator. We also know what? We know EP is 2. Right. So if EP is 2, if EP is 2 and E is 3, then 3P is 2. What does this tell us? P is 2/3. What is P? What does it mean? Look back at your diagram. Distance from the directrix to the focus. Or you could say the distance from the directrix to the pole or origin. Good. Okay, so I think we just figured out where our directrix is. If this distance is truly 2/3, and it is, then we know that the equation of the directrix is x equals negative 2/3. This is the first thing they asked me to find. So I'm going to get up here and write x equals negative 2/3. I found my first thing. Okay, feels like success. vertex. Well, the vertex is fortunately one of the many points on the graph. Isn't that true? There are thousands of points on a curve, but the vertex counts as a point, doesn't he? Sure he does. Some they say he's really important. I'm not sure he's super important, but he is definitely on the graph, and he should obey the rules we saw back in Act 2 yesterday. In other words, if the eccentricity is 3, mathematically it means this. The distance from the point to the focus divided by the distance from the point to the directrix is 3, is what it means. Or you can think of it this way, multiplied by dpd. So dpf is triple what dpd is. That's another way to write it. You just multiply it over. And isn't it true that, well, isn't it true that the vertex is one of our points P? That's true, right? So can I just change the P to a V real quick? Is that cool? He's one of the points on the curve, isn't he? Okay. So listen, what I'm saying is, this is very important. It's very subtle. Not easy to catch this. You see these two segments here? This one and this one? Is that too light? That's too light. Let's get a darker blue. See the gray and the blue? Their ratio is 3 and 1. That's what it means. All points on the curve obey this rule. Vertex included. So that distance is triple what that distance is. Make sense? Triple. Okay? So let's say that this distance here is, I don't know, give me a letter of the alphabet. S. Let's say this is S. I'm sorry, let's make the little guy S. This little guy is S. This would be 3S. That's a little too small to see there. Sorry about that. This is where you might want to draw like a diagram too, you know. We'll do the purple. This is 3S. This little distance is S. Right? You said S. Okay, so that's 4 S's. Right? And together it makes 2/3. See it? 3S, another S makes 2/3. Okay, so we can solve that. We can write the segment 3S and the littler segment S makes 2/3. In other words, 4S is 2/3. In other words, S is 2/12 or 1/6. So S is 1/6. That's a hard calculation. But it tells me where my vertex is. If S is 1/6, then 3S is what class? 1/2. We got 3/6. Right. So where is Mr. Vertex? Yeah, that's right. This distance right here is 1/2. So that means it's the point -1/2, 0. Okay, so it's time for diagram 2, don't you think? That thing was getting kind of cluttered. Here's what we have so far. Here's our focus. It's at 0. Here is our directrix. It's at x equals -2/3. I think I put it out there too far. We need some more space over there in a minute. Let's put it right here. This is -2/3. That's our directrix. We knew that the vertex was somewhere between them. We split this distance between them into 4 equal parts and dedicated 3 of those distances to the VF segment and only one of them to the VD segment. In other words, this distance was 1/6. This distance was 1/2. So we declared our first vertex to be at -1/2, 0. The curve, remember, goes like this. Okay, what shape was this again? The hyperbola, right. Doesn't that mean there's another vertex somewhere? Ooh, that's scary. Okay, well, here's where things get really, really complicated, and I'm going to teach you a way to cheat your way around it. It turns out there's another directrix. In fact, this whole image needs to be reflected. Okay, watch Mr. Sharp. I'm just going to demonstrate with my body. So this whole thing is going to go like this. Bam. There's going to be another half over here. The directrix is going to copy itself over too. There's another directrix over here. Okay, here's a very common student error. They assume that there's one directrix and that the other vertex is 1/6 of a space on the other side. That is false. The problem is the center is over here somewhere, and then there's another directrix, and then out further there's another vertex. So it gets pretty confusing, especially if I start drawing a second directrix. You're going to be like, I'm done. So here's what I'm going to let you do. Here's what I'm going to let you do. Now that you know at least that all conics have a directrix, and you now know how to examine polar form, I'm going to let you make a table. Okay? You might say, I hate making tables. Trust me, it's better than the alternative. All right? We're going to make a little theta r table. Okay? You're going to pick your favorite thetas. I highly recommend only multiples of 90. I highly recommend only multiples of 90, or you're going to get yourself in a real mess. The function was, what was it again? 2 over 1 minus 3, right? Okay. Okay, yeah. So if you plug in 0, you're going to get 2 over 1 minus 3 times 1. In other words, it's going to come out to negative 1. If you plug in 90, it's going to be 2 over 1 minus 0, because cos 90 is 0. So that's just 2. If you plug in 180, it's going to be 2 over 1 plus 3, which is a half. And if you plug in 270, it's going to be 2 over 1 minus 0 again. That's 2. So a couple of these are duplicates. You know how that is. Anyway, the reason I let you make this table is because it quickly answers some big questions. Okay? Okay, remember, these are polar points. Polar points. So you have to think of it like this. You're going to plot the point negative 1, 0 degrees. And you're going to plot the point 2, 90. And you're going to plot the point half, 180. And you're going to plot the point 2, 270. Okay? This is why you might want to use polar paper for this weekend's assignment. I have some still if you want to come grab some after class. Okay? But honestly, these aren't too hard to plot even on regular paper because they're all multiples of 90. So let's go back to our drawing and let's plot these guys. The first one to plot is 0 degrees, negative 1. So 0 degrees, negative 1. Let's see, where would that go? Because 0 degrees is here, but how do you plot negative 1? Like, do you go towards the 0? No, you go backwards, right? You moonwalk. So 0 degrees, negative 1 means you're actually going away from the 0 degrees mark one full space. Well, that's way over here. We would call this, in Cartesian world, we would call this negative 1, 0, also known as negative 1, 0 degrees. What is that point? Well, no, but then the center wouldn't be on the graph like that. This came from the table. He's one of the points on the graph. No, he's a point on the curve. He's our other vertex. Yes, he's our other vertex because he's part of the curve. You see, foci, directrices, those guys aren't on the curve. Vertex is. He's our vertex number 2. Okay, so we got our vertex number 2. We just found our other vertex. It was weird finding it. Let's go back in the title. I said find the vertices. We now know the vertices are at negative. Let's see if I can fit this in here. It was negative 0.5, 0, negative 1, 0. Those are your vertices. Yay. Okay, back to the drawing board. How did I get that second vertex? I cheated and used a table. Yes, I did. Okay, 290. Let's find 290 on the graph. So that's basically in the 90-degree direction, you go up 2 spaces. Oh, that's our y-intercept. My scale's a little weird. Uno's on the x-axis is way over here. But that's 2 on the y-axis. I couldn't go any higher off the page. So this will just be distort it, but you guys see that? Evidently, the point 02 is a green point. That's what our table's telling us. So that means that's where the hyperbola hits the y-axis. So that guy's a y-intercept. Let's go back to our table. So we just graphed this one. We just graphed this one. Let's graph 1/2, comma 180. 1/2, comma 180. 1/2, 180. Let's see. 180 is over here. So that's the direction of travel. We're going to go half a space over. Yeah, this drawing's worse than I thought. You guys are laughing. I realize now why you're laughing at my little picture. Mr. Short put -1, very, very close to -1/2, right? Okay, I see why you're giggling at this. So let me fix it real quick. Let's shrink this whole picture down. Oh, the wonders of modern technology. There we go. Okay, so you guys are kind of laughing at that. If this is -1/2, I can see why you're laughing. -1 should have been over here. And this is our other vertex. We got that by cheating and using the table. Okay. Okay, so we were just trying to plot 1/2, comma 180, right? Well, that turns out to be what point? Which vertex? The first one we found. Right. Okay, so listen. It's going to be a huge cheat to just make a table. Do you remember how hard it was to get this vertex in the first place? We split this distance into 4 equal parts. We dedicated one of the distances to be over here. That was s equals 1/6. This is s equals 3/6. Remember that? I still want you to find the first vertex the way I did. Because making a table is the biggest cheat ever. A ninth grader could do it and not understand a thing. You need to understand it. So I suggest you at least find the first vertex like I did by splitting the p distance into 2 predetermined ratio pieces like I did. 3 and 1 in this case. Please do that, okay? Alrighty. Okay, anyway, we got both vertices. We can go back and title that. So -1, 0, -0.50, we already had that. Oh, we need to find the other focus. It says find the foci, right? Well, we know one focus is at 0, 0, naturally. But where's the other focus? Let's go to our picture. What do you guys think? -1/2? No, that's right here. -1.5. Yes, that's correct. Because it's a half space from this vertex to this focus. So you would then go from this vertex back a half space to get the other focus. So I'll draw the foci in red. They're not really part of the graph, you know. So our other focus is over here at -1.5. Okay, so going back and titling this, we have foci at 0, 0 and -1.50. It should be pretty easy for you to find the center. The center. It's got to be halfway between the red dots or the green dots, your choice. Well, it's halfway between 0 and -1.5. -0.75, right. So the center is going to be right in the middle at -0.75. So I'll do that in blue. I'll just put -3/4, comma 0. Intercepts. Well, we've done pretty well with that already. We know the x-intercepts. Those are just the vertices. So I'll write my intercepts on this page. The intercepts are just the vertices, -1, 0, -1/2, 0. Those are the x-intercepts. Then we have the y-intercepts. We got one of them from our table. It was the point 0, 2, remember? And you can obviously guess by the symmetry alone that the other one is at 0, -2. Actually, I don't know if you noticed, Mr. Short forgot to plot this 4th point. He's our other y-intercept. He's our other y-intercept. So there is your grand conclusion on the first example of polar form of conic. This one's done. That's a lot of work. I'll bet you can tell me where that other directrix is now. Yeah. So right now, this is negative 1/2. Awesome. Yeah. So remember this little distance was 1/6? That was 1/6. You told me to call S, remember? Okay. So this is 1/6. And so if you go over here and you just go 1/6 backwards, this is negative 6/6. So it'd be right here, negative 5/6. Yeah, you're right. Good. So the other directrix, it's pretty hard to explain like how to draw using both directrices. So what I usually teach my students is to let them cheat right when they get to this first vertex. They've done all that hard work already. You've learned enough. Bust out, use a table, get your points. You can find the rest of the stuff pretty easily. Okay? I need to ask you a couple what if questions before the bell rings. Okay? What if Mr. Shore gave you this problem instead? 4 over 3 plus, 4 over 2 plus 3 sine. There are some major differences between this problem and the one we just did. There's one difference that's so great, we have to fix it before we're even allowed to start. It's not the sine. It's not the plus. You're right, those are different. That 2 shouldn't be there. This has to be the 1. Very, very important. It's like in the standard form, you have to have the right side equal to 1. It's that important. So we need to first divide this, and this by 2. We're not changing the problem. We're making this work for us. Okay, you're right, though. The last problem we did had a minus here, not a plus. But I'll bet you could tell me what that does to the graph when I change the minus to a plus. What do you think? So she did this. Yes, instead of our first sketching going to the right, it will go to the left. Okay, so it's going to be a backwards thing. Ooh, but the cosine has been changed to a sine. Didn't we talk about that, though, in polar chapter? Back in chapter 8, we talked about that. Changing signs on like a rose. Remember on the rose? You change cosine to sine. What happens? Right? Okay, so do you guys want to guess with me what this would look like? Okay, so it's no longer sideways, right? It's up and down. And the first thing you draw will be one of the branches of the hyperbola, right? Are you going to draw it going up or down? It's actually going to be down. Okay, so if this confuses you, listen, page 714 says it all. Page 714 in the book. It says that if you have EP over 1 minus E cos, then your conic looks like this when you first start drawing. If you have EP over 1 plus cos, EP over 1 plus E cos, then it looks like this when you first start drawing. Okay? If it's a sine instead of a cosine, then there is a rotation, a 90-degree rotation involved. So if you have a EP over 1 minus E sine, then it's an up drawing. And the last case, of course, is the down drawing. If you have EP over 1 plus E sine, it's a down drawing. They all have the focus at the pole. They all have the directrix, okay? They all have the same basic look to them. It's an orientation thing. So cosines are sideways and sines are vertical, and plus means either left or down. Minus means either up or right. Okay? So don't be too confused. But the one thing that isn't obvious, I think, is how we had to divide by 2 before we started. That's super important. By the way, is this hyperbola again, or what is this thing? 3 halves. Is that bigger than 1 or less than 1? Okay, so this is greater than 1, right? 12.5. So it's what? What kind of shape is it? Hyperbola. If that was a 2/3, it'd be an ellipse and so forth. All right, have fun with it. It's kind of fun. I have polar paper. You can always cheat and look at your calculator if you really get stuck. But try to do as much as you can without peeking. Monday we start vectors. That's a 2-week unit. Take your book home. It's a book page tonight.